TNRP, I'm going to say these are continuing past October 1st, and Tom will be talking about how we're going to be building out using those. Okay, somebody needs to ring a cowbell.
Well, she's got a glockenspiel out there. Maybe give it just another minute
Sure.
for people to get settled.
I'm a professor. I'm used to late classes.
Okay, so we'll get started just about on time. It is my great pleasure to welcome our next panel to talk to us today about Nautilus and the National Research Platform. And I'd like to first introduce the distinguished professor, Dr. Larry SMARR, and he'll introduce the rest of the panel. Thank you.
Hello. As they hopefully assemble a little more audience out here, I'll just tell you an overview that we're going to talk about is the evolution of the Pacific Research Platform, which has been underway for 7 years, into the National Research Platform. The Pacific Research Platform, which I assume a number of you are familiar with, grew out of the existence of SENIC, not only technically, but maybe even more importantly, socially, because I was a member of the board for almost 20 years. The SENIC is the one place that has brought together all the different research and education entities. And as things were developing where, as we heard the other day, data is the new currency. Everybody's getting into data, getting into networking. Now we're seeing getting into artificial intelligence. There needed to be a platform that could make that available, for instance, to all of the SENIC partners. And so we pulled together a proposal to the National Science Foundation, which was funded, and that started in 2015. And 3 days from now, after 7 years, the Pacific Research Platform grant will be over. What this panel is about is to tell you that that's just the caterpillar phase, and there are several more grants that we've gotten which will continue this into the pupa phase, and that's Tom DEFANTI, who will talk about that. And then out of this is going to emerge a beautiful butterfly, which is Frank Wertheim, the director of the San Diego Supercomputer Center and the executive director of the Open Science Grid, which I'll talk about briefly. And so this is really the announcement of that transition, which has been underway for a long time. And this will, then with the National Research Platform, this will be around for quite a long time to come. Now, the thing that made this distributed infrastructure possible for computing and storage was the PC revolution, of course, and the ability to have gaming cards in a rack-mounted PC, but also to be able to connect it at 10, 40, or 100 gigabits per second. And so these things are commodity, but they get faster and cheaper every year on hundreds of millions of people buying them, which drives the technology curve, and that's why, of course, we do it. These are standardized, specified, and on our website, our Pacific Research Platform website, we have the specifications, so everybody can just order these and install them themselves, when of course we provide a lot of help for that. By now, we have over 160 of these GPU and storage, these individual, what we call Fionas, Flash I/O network appliances, can hold up to 200 terabytes of rotating storage. So when you put them together, over 27 partners, all interconnected at these speeds of 10 to 100 gigabits, we have all, this is as of a couple of days ago, we have 8,600 CPU cores, 627 GPUs, and these are the gaming, 32-bit gaming GPUs that, you know, they're shipped 50 million a year. So those are very cost effective and are actually much more appropriate than the 64-bit sort of gold-plated GPUs that are particularly for machine learning, where the data isn't double precision, and over 4 petabytes of storage. And all of this exists on the Scenic, Quilt, and Internet 2 network backplane. Now, the big thing that made a lot of what we're doing possible is a sort of reverse engineering of what we were used to, which is, you know, when I was director of NCSA and Mosaic came out from the academic world and from CERN, the particle accelerator, it then led to, you know, eventually the world we know today, and probably an extra $1 trillion or something to the global product. So we always assume that innovation comes out of universities and then companies adopt it. But actually, we're in a different phase these days, where as a result of the build out of that giant infrastructure, global infrastructure of the web, now it's the cloud providers that have to do 1 billion searches a day, like Google, that have containerized their software because it has to be fully automated. There can't be any humans in the loop if you're doing 1 billion a day. And their PCs connected by optical networks, which is just basically what the PRP is for academia, that's the cloud, is global. And so they have to be able to move these containers around and execute them completely automatically. And to do that, they developed something called Kubernetes, which orchestrates the movement of these software containers. And those are basically, again, you take your user application, you containerize them, and then Kubernetes takes them and moves them to an executable PC node, which can either be on the Pacific Research Platform or in the cloud. And all this is through the Cloud Native Foundation that is open source. Well, this is, I mean, I always thought something like this would eventually happen. I just didn't think I would live long enough to see it. And I'm so happy that I did. But we, of course, adopted this for the PRP, and this is what we call Nautilus. That is, this is a software infrastructure across this network set of PCs that enables us to not only use Kubernetes to orchestrate the movement and execution of software containers, but because something called Rook sits under and runs under Kubernetes, that organizes the storage, which comes out of Santa Cruz, thank you, Jeff, and your predecessors, who made Ceph. And so as a result, we can, even though we just have a small number of people on our team, we can actually orchestrate thousands of terabytes of data across the country, and we have now over 700 applications using this distributed infrastructure. And we break this storage because of the network, because of the speed of light. You have to actually break the country up into multiple regions that are only so many, milliseconds, hundreds of milliseconds across from a light travel point of view. So we actually have a Pacific pool with Guam and Hawaii. We have a Western pool. We have a Central pool. We have an Eastern pool of storage. What that does is that allows the user to sort of place the storage of the data that they're going to execute on closer to where the computing is actually done. This is, again, something that is because of standards, the stuff that makes it all possible under Rook, under Kubernetes. Now, a lot of people come onto the PRP as users by themselves using the documentation that we have on the PRP website. And it's odd that we actually care about documentation as people who write programs, but this is actually a pretty good job. And so you can figure out how to get access, how to use CI login, which is what all the campuses use for authentication, how to containerize basic Kubernetes, and then all of our users form a community of practice of help to all the others. So there's a matrix is our chat basically, where you can throw out a question and you get answers. Jupyter notebooks are where a lot of the electronic notebooks that people use are, then you can share those with each other. And all this goes through GitLab, which allows for constant updating of the software system as a whole. And again, for those of you who are interested in security, this is built on the Department of Energy's DMZs. Each campus has what's called a DMZ, which is a separate security network from the commodity traffic. And you can read many pages about how secure that is in the ESNet logon. Again, we use CI login. We have namespaces which allow you to have multiple people on your project, but that doesn't interfere with anybody else's project, and you can't get into each other's project, so it's secure across the PRP. And then we use things like Calico for policy-driven network security, and Elastaflow for doing all of this, all of the networking, all of them. Everything is instrumented. We actually know the fan speed and the temperature of every one of these Fiona's PCs across the whole network in real time, all the time. We know all of the networking, where all the routers are, if there's anything goes wrong. So that is what has been built up over the last 7 years in the PRP. But then 2 years later, from 17 through 20, we got this thing called Chase CI, which adds a machine learning layer to all of this. And Tom is going to take you more into the 2 follow-on grants for Chase CI that we have that are now enabling us to distribute across the country to many minority-serving institutions and others to participate in all this. And then a year later, we got another NSF grant called Toward the National Research Platform, TNRP. And what that allowed us to do is to go from the original regional networks that we had in Scenic, the Pacific Northwest Gigapop, the Front Range Gigapop, and IMRIN in Chicago, and extend that to include the Midwest Great Plains Network, the Texas Learn Regional Optical Network, NYSERNet in the Northeast, and KINBER in Pennsylvania. And of course, Internet too has become a really major component in tying all this together. And you see this on the map of the quilt because we have many of the other regional networks in the quilt that also are part of this. Now, Frank is executive director of the Open Science Grid, which is a separate distributed infrastructure which consists of clusters all over the country and all over the world that that allow for a single fabric, the Open Science Grid, for high throughput computing. And that's where a lot of work in science and data analysis is done all over the world, including the Large Hadron Collider, LIGO, and other big instruments. And it's amazing. It actually produces over 2 billion core hours a year delivered to end users. So it's an amazing resource, and the ability to federate that with the PRP is huge. And that's why I wanted Frank to be the co-PI back 7 years ago. It was clear to me that if the PRP succeeded of hooking all these campuses together, it needed to federate with the OSG. And I'll just point out that when I was director of NCSA, I delivered in 1990 about 35,000 core hours, and OSG now delivers 2 billion a year. So the OSG can, because it's federated, reach into the PRP and get the GPUs that it doesn't have as many GPUs. And from Frank, we've got that 1 million GPU hours on the PRP were used through OSG by their users. So it sort of flows from one to the other. Now, I hope that many of you will be able to look at the video that we produced, the PRP video, and you just search for it, Pacific Research Platform video, and you'll find it on our website, because that gives you 3 good examples, and the video does it much better. I can't take you in this time we've got through them all, but they're quite different ones. IceCube, the South Pole neutrino detector from the NSF, hooking VR, virtual reality systems together, and Wi-Fi. And I'll just give just one slide on each. This is the South Pole neutrino detector, and what happens is when a neutrino actually finally interacts with an atom in the ice, it sets off a photon cascade, and so you need to calculate the photons moving through the ice in parallel, and that requires something like 300 or 500 GPUs for many months at a time. And so it's a huge thing, but that doesn't displace anybody else. It just, if those are available, it grabs them. And so that's one of the nice things about the infrastructure, is that it can be made available. Another nice thing about it is we have these virtual reality facilities. Jeff constructed the Wave at, when he was at Merced, and then Tom designed the Sun Cave at Cal IT2 at San Diego. And the first thing we did was use Scenic to hook those together and be able to have the same thing show up in both caves at the same time. But then we realized that we had something like 90 GPUs running those two, so we just added that into the pool of GPUs on the Pacific Research Platform. And you can see all of this in beautiful motion in the video. So again, I really hope you can take time to look at that. And then in Wi-Fi, Ilkay Altinus, who spoke yesterday on our panel, is a person who's one of the leading people in the country on developing workflows. And so she's able to take all the real-time instruments, the cameras and the meteorological instruments that are in Southern California, and bring them into the workflow along with all the weather forecasts, so we know where the wind's blowing, everything. And then we develop into that a fully three-dimensional model, a digital twin of, in this case, Southern California, with lots of different layers as to both the topography and then the fuel load and so forth. But from air assets, both airplanes and drones and so forth, we know where the fire perimeter is. All that workflow then uses something called FireSight, which is a fire modeler on the San Diego Supercomputer Center, and then that data goes back into the workflow and out into a public-facing website, which has had over 1 million hits by citizens. So this is a very citizen-focused project. Well, I'm just going to end by saying that, you know, we sort of hoped it was going to work when we started 7 years ago with a PRP. We started with 5 states, 6 states. We're now in 40 states. This is the number of people who actually have logged on and used the PRP. We've gone from 19 campuses to 95 campuses. We've gone from 9 minority serving institutions to 20. And we've gone from 2 EPSCoR states, the bottom half of the states, they get the least money from NSF, to now 19 of them, plus 2 territories in Washington, D.C., all in 7 years. But we're just starting. We've shown it all works. We've got a robust community, but going back to the theme of this conference, the minds we need that do not have access to the GPUs they need to do machine learning, for instance. And this includes, we currently have all 10 of the UC campuses. We have, amazingly, 6 of the 23 Cal States that are users, and the green there are minority serving institutions. We have the 3 privates plus Harvey Mudd and the Naval Postgraduate School. But where we're going, and this is where we really could use your help, is the rest of the scenic community. There's 17 more CSUs that haven't logged on yet, haven't got a user. Community colleges, many of them run planetariums. There's really a whole new workflow. Think of all the community colleges that should be turning out people who know how to run machine learning, TensorFlow, PyTorch, be able to use a Jupyter Lab. Where do they get GPUs? Not at the community college, but because all of these libraries, planetariums, museums are hooked together with scenic. Anyone in those has access to this. They all of a sudden are empowered. They are the missing minds. They are now able to work just as much as if you're at Caltech or Stanford or UC San Diego. So, as we see that PRP switch into the NRP, this will continue, as I said, for a long time. And what Tom is going to do is talk about the near term of reaching out to many other, particularly minority serving institutions across the country. And then Frank is going to tell us about the National Research Platform. So I'll stop here and turn it over to Tom.
Thank you, Larry. Let's see, first slide, please. Am I supposed to, oh, I'm probably supposed to do something.
They should just bring it up.
Is it this button you push?
The green go button.
Okay.
Yeah,
Oh,
there you
that's
are.
good. Celebrate explosions. A few years ago, about 5 years ago, we started building these Fionas into places, and this is what it looked like. At the end of the first phase, 14 campuses, 3,000 CPU cores, and 300 GPUs. And what we basically did to do this is we ran around the state. I literally drove these boxes around in the back of my car because I realized that in order to get them to be installed and not just sit on the floor until somebody got around to it, it was a real good idea for John Graham and I to stand there and watch people plug them in, right? And then solve any of the problems. And so we did that. In about a week, we got all of these boxes installed. So that was kind of our model. All in people's science DMZs and all with friendly faces. Now, Frank WÜRTHWEIN, being a physicist, simplified all of our thoughts into a few statements. Why does this work? Why does Nautilus scale? And why does it fit our researchers? The simple observation about computing capacity, at least the way we do it, is that it scales linearly with cost at any given time. That means that if you buy twice as much, you get twice as much compute power. And if you wait, basically Moore's law style, if you wait, it scales exponentially at a fixed cost. So it means you spend the same money, later you get much more capability. But the human effort to support this is more of a logarithmic function in that it doesn't scale linearly. It scales a lot less than linearly, and particularly with all the automation we've put into it. Now, this is a key thing because faculty members in particular can write proposals and get equipment pretty easily. Asking the National Science Foundation or anybody else for full-time staff to maintain things for the next 5 years is essentially impossible. It only happens in very rare cases of huge grants. So the idea was for us to take on that burden and to help people, because a campus, a community college, a CSU, whatever, in order for them to say, well, we're not going to do what, you know, Dell tells us to do with Microsoft and so on, but we're going to try and set up a Linux cluster with Kubernetes and everything else. This is a huge step forward for them to do that. And we do it, essentially do it for them, and then they start teaching people how to do it. So this is now turned into what Frank's going to talk about, which is the National Research Platform and its prototype. So this is the what things are like this fall, is it will have now gone up to 1,100 GPUs, which is almost 4 times as many. And these include a couple of ARO DURIP grants and the new 384 GPUs from the PNRP, Frank's grant that I'm part of. And you'll notice in our clever color coding that Charles Irwin came up with here, that you can see which ones are EPSCoR states, which ones are minority serving, and which ones are, you know, essentially non-official minority serving institutions. And this was our goal. Our goal was really to take this out of California, having proven and gotten essentially everybody who wanted to play with us initially, and then move it into the Midwest and the East Coast, just like that. And it's worked rather well. Now, in order to do this, we've had to get all the help from various of the networks. This is a very network-centric thing. The networks have to make this work. We have to get MTU 9000 across the networks at 10 and 100 gigabits a second, and that's not everywhere. It isn't everywhere, but it's a lot of places. The responsibilities for this particular grant, as UC San Diego, is focusing on the innovation, hardware and software, and putting in new devices like FPGAs and 5G capability. A lot of that 5G capability now works on these small FPGA cards that Xilinx makes that allows us to go from the radios to the fiber. UC Santa Cruz and Jeff Weekly with his advisor, Dr. Kurniawan, is officially, and she's their computational media people, and they are basically in charge of evaluating all of the onboarding materials and instructional materials we use, and developing new ways of doing that. That's their specialty. University of Nebraska-Lincoln is taking over the day-to-day system administration as part of what they're doing and growing a group there. And then we have people at Florida A&M, University of Illinois Chicago, NYU, San Diego State, Scenic Internet 2, other places that are hosting. Hosting is real important because the cost of providing these computers, the equipment we get from NSF, the real cost in this is the power. These things consume as much power as they cost, and that's a big deal. Also networking and rack space, and UC San Diego is simply not going to do this for the rest of the world, you know, so it was important to share it, to make it so that everybody had a piece of it who wanted to. So let's go on. So then on top of this, the central part of the PRP was not computing, it's data movement. That was what it was funded for. And so we started putting these 200 terabyte servers all over the place. Now they're fairly cheap. They're about $13,000 a piece for 200 terabytes. And again, you know, people are providing the power and the networking for them. And we've put them into these Ceph pools, as they're called. And they work very nicely regionally. You have to be, I don't know, 10 milliseconds away to work with the systems and not give you undue delay in getting your data. But it's clever because we've kind of moved from this concept of working throughout the country to make sure that the internet could run 10,000 times faster than when we started, and that's not an exaggeration, from 5 megabits a second to 50 gigabits a second. But having done all of that, by having these Ceph pools in the right places, you don't have to move the data. You can just essentially grab it directly, run it directly. That's a big deal. It's a big change. And we need more of these Ceph pools because there's some places like the Pacific Northwest and the Southeast that we don't have them yet. So, and Texas area, we don't have them yet. Now we measure this stuff out the wazoo. A lot of what we get paid for when you write an NSF grant, especially in the networking domain or really in any advanced cyber infrastructure, they want to know what they're paying for and why, and so you do measurements. And so we use a lot of Grafana, and you can see in this one is that we pretty much know everything about every one of the users and what they're doing and when they're doing, and we ask them to give us content and publications, and we tell them this is all public, and that if they're going to use it, we're going to tell people about it. There isn't any confidential issues here or personal identification stuff we have to worry about. And you'll see these are, Larry builds these charts, and this shows you a variety of major users here, the top 15 of the GPUs, and you'll see that it peaks up to 500, which is what we've had until very recently. We've popped over 600. And similarly on the CPUs, you know, we're getting thousands of CPU cores being used by projects. Now, you know, these things are very spiky, you see this, and this works out very well with the systems because all of the black area there is what IceCube comes in and uses when nobody's looking. I mean, it really runs in the background. And so that's the whole idea for the OSG jobs, to be able to run in the background, which is what they're used to doing. And it keeps the computer rooms nice and warm. Okay, so how do we get access to it? So we use a thing called CI Logon, which is essentially a triple authentication software that most campuses are partnering with and gives us a single sign-on. We can also let people in with Google credentials, but we tend to do it one by one. If their campus doesn't allow this, it doesn't have CI Logon. Otherwise, we get classes signing on from Sri Lanka and other kinds of things. It's the key to our federation, and the CI Logon people made changes to allow us to do what we need to do. Very, very, very helpful. And like I said, we're building these things now into 4 regions as well as the Asia-Pacific islands, Hawaii and Guam. And I've talked about the other things about Ceph, but this is a major achievement, I think, to have this distributed storage so well integrated with Kubernetes and with the computing. We spent a lot of time with the, did I go? Did I miss one? Let's see. No? Okay. Oh, no, I'm looking at the wrong one. So the social diversity has been an issue that we've tried to address, and this has worked out pretty well. A lot of our universities now, as Larry pointed out, are minority-serving institutions. You know, most of these CSUs in California are minority-serving institutions, 23 out of 25. Half of the UCs are minority-serving institutions. And then there's this, you know, that this is outside of California, there's this a group of states called EPSCoR states, which are the ones that are underfunded by NSF. We've also made a real push to get more women involved as PIs, as students, and so on, and training people to take over. We support undergraduate education in various places, and it turns out the undergraduate users are very peaky in twice a quarter or twice a semester. And so we can pretty much absorb them without any issues. And for the campuses that put up instructional systems, like for instance, San Diego State, the idea is to share them for both research and instructional labs. And that can work quite well because Kubernetes basically handles it. The other thing about Kubernetes is nice is that when machines drop dead, they just get thrown out, until somebody fixes them or you ignore them forever. And you also get the I mean, that really helps, and then it's easy to add machines. And for things like the Sun Cave, which has 70 GPUs, anytime we start it up and use it for visualization, all the jobs drain out automatically, and then when we're done, they all come flooding back in. So we can do this for anybody. Anybody says, well, I don't think I'm getting everything I put into it. Okay, we'll just lock off your machines until you're happy. It's very easy. And we had to do that to get people to play with us. We're finding our students are getting routinely stolen by industry, which of course is what we're supposed to do. We're supposed to take undergraduates and graduate students and teach them this stuff and get them real jobs. And that's working very, very well. So ENS and what we're doing is enhance and sustain. We're enhancing it, obviously. We're also working to sustain it with high levels of automation. And we call this, I call it potluck supercomputing. Frank calls it bring your own resources and devices. And we also have a trial version we call Soup Kitchen Supercomputing. I do anyway. And I'm happy to talk to people later on at lunch or during the Q&A about how, why we think this can actually survive. Why can it live? Why is it a model that is extensible and clonable, and how people can have their own, Nautilus system if they want, or join with ours. Okay, so we're community building now through these workshops. So we had one 5 years ago. First one in Montana, the second one in Montana, and then we did one in Minneapolis, the third one, and then we skipped the pandemic and are doing another one in San Diego in February 8th to 10th. Hopefully you'll hear about it, and I hope you come. And it will really be fundamentally focusing on what Frank's going to talk about next, is what's the next 10 years. I want to also tell you that there's Allied workshop, APRP, in Singapore in February. And the second, there's also been a global research platform that is largely integrating all of the research platforms that are formed kind of on our model around the world. And they will have a meeting in a couple of weeks in Salt Lake City. So, and I will end this with our mandatory thank you slide to NSF for all the grants we've gotten over the years and the various people who have supported us and when we've asked. And it's over to Frank now. Thank you.
Okay, my name is Frank WÜRTHWEIN, and I'm the director of the San Diego Supercomputer Center. And I'm going to talk about NRP for the next 10 years. You've heard that Larry just announced that PRP is sort of falling off a cliff in 3 days from now. NRP has actually already started. We literally have moved responsibility over from one project to the next seamlessly. Nautilus is the a cluster that will host all the new hardware that we're currently deploying. And I will tell you about how this comes about, but first I want to start a little bit back and talk a little bit about the vision. What's the bigger vision behind all of this? And the vision goes, of course, ultimately back to democratizing access. You've seen this as a picture, I think half a dozen times maybe by now in this week, in various different talks. And I want to point out to the bottom half of this, this is literally verbatim from the Minds We Need website. I didn't adulterate anything here, I just took it straight from the website. And what I find important to note is not only is this about equity, justice, and alike, it ultimately is about industrial competitiveness. If you think about this for a second, the only way that as a society we are competitive with the rest of the world is if we actually use our human capital to the best of our abilities. And to the best of our abilities means access for all, finding the geniuses no matter where they come from and making it possible for every individual to get to the best they can be and they want to be. And so if this is ultimately the goal, then here's what I think of as the vision long term. There's about 4,000, there's actually 3,900 accredited degree-granting higher education institutions, and then there's about another 100 or so non-profit research institutions and national laboratories. So let's be rough and call it 4,000. I'm a physicist, we work in rough numbers. So there's roughly 4,000 institutions that we would like to federate with. In other words, those are the targets that we want to work with in some kind of fashion and creating an open infrastructure that does open science, uses open data, is implemented in open source, and ultimately has open compute devices, open storage devices, and open other devices. In particular, I want to point out that the frontier, so to speak, we've already done open compute and open data. You've heard that from Tom and Larry. I think the frontier on some level is to go beyond this and think about, can we actually extend what we do today in interesting new ways via wireless, via IoT, via edge computing, via sensor networks, and use all of these kinds of different kinds of devices and build a national, eventually global infrastructure where all of these devices can federate, all of these resources can federate and create openness for an open society, and do this both horizontally open and vertically open. Where I mean horizontally open, everybody can join, and vertically open, everybody can build upon it. Meaning we not only want to have scientific or other useful use out of this, societal use out of this, training, teaching, whatever. We also want people to have the means to build service infrastructures on top of it. The beauty of Kubernetes is that you can deploy services. You can build on the substrate that we are supporting in interesting and novel ways and support new kind of capabilities. So we're as much interested in the quote-unquote end-user scientist as we are interested in the quote-unquote systems builder. And our platform ought to be a platform that both can benefit from and can work with each other and help each other for doing new and interesting things in the future. Moreover, I want to point out that this isn't about funded projects. We are building a community, and the community is seeded and partially sustained by an NSF grant. It by no means is just a project that is funded by the NSF. We take the money and run, deploy something, make sure that people use it. I look at this much more as a community support organization. I look at it as a community that ultimately grows over, and CNIC is a particularly interesting place to talk about this because CNIC is such a interesting stakeholder community. It reaches to K-12, it reaches to the libraries, it reaches to all kinds of places that are expanding beyond just the academic environment of colleges and universities. And so what we want to do is we have a community with a shared vision, and then we want to be available for lots of funded projects that contribute to this shared vision in different ways. And we want you to grow NRP and build on NRP, bottom line. So NRP is owned and built by the community for the community. That's basically the message that I want to send. Then supporting Nautilus for the next decade, there has to be, in order to build a community infrastructure like this, there has to be something that seeds some minimal sustainability in order to, such that the platform is available so that others can build on it. And that minimal supporting infrastructure is provided by an NSF grant via the Category 2 program. I wanted to explain a little bit what this Category 2 program is all about, and then show you what we're building as part of this. and this is then the seed that will keep this going for the next 10 years. And I'll explain to you, because the program characteristics of the Category 2 program allows us to do this for potentially 10 years. So what's the program about? NSF supports, via the Category 2 program, novel system ideas. It's funded out of OSC to stretch the envelope. Think outside the box. That's what it's meant for. It has a 3-year testbed phase where the PI is in full control and doesn't have to necessarily dance to an allocation mechanism. We can figure out what kind of allocation makes the most sense, and we can community build. We can use the hardware paid for by the NSF to support this community building for the first 3 years. And then there's a 2-year allocation phase, at which point 90% of the hardware that was purchased with NSF funds gets allocated via some allocation mechanism that we join. And there's, off the bat, 3 different ones that we could choose. There's the access, formerly Exceed. There is something akin to what Path is doing now, the Path facility. And then there is the kind of thing that a Chameleon do for the systems builder community. So there is actually multiple different kinds of allocation mechanisms that use different software environments that we will try to see whether we can actually work with, and how much headache it is to support different kind of allocation mechanisms on the same hardware. Because different communities work with different interfaces. That's the goal. And so we decided that this kind of program is an ideal program to try and secure an NRP core operations funding for the next 10 years, in part because it gives you a 5-year funding horizon, and then has stipulated into it that there is a possible non-compete if you are deemed worthy. And so you can get a second 5-year after the first 5 years, so potentially this can actually support NRP for the next 10 years. That's the plan. So now what is it? What have we actually gotten funded? We've gotten a 5-year project with about $5 million of hardware and $6.5 million of people money. The actual hardware that we've bought and that is currently being deployed, literally last week, things went up. And 2 of the 3 sites that have the main hardware went up last week. That is San Diego and Nebraska and Lincoln, and Massachusetts goes up on October 4th. Now, in addition to the 3 main compute sites that we deliberately chose to span the nation, southwest, middle, northeast, we're working with Internet 2 to put into their POPs, and I went at this SPI by taking a map from Google, making circles of 500 miles, and then asking myself, how do I tessellate the country with circles of 500 miles and place caches in POPs of Internet 2 in order to map the country? I wanted to have a system, you can think of it as a content delivery network if you wish, a system of caches inside the network backbone such that every place in the country, at least the continental USA, is within 500 miles of a cache. And I'll talk about how this works in terms of data model in a second. And then you can see that it's not perfect. There's some sort of gray areas between the circles, and we're sort of filling some of this in with other funds. The very tip of Florida that I'm hiding here, for example, is empty, and we're working with partners to place something in Miami to fill Florida from the bottom up, and other things like this. We're placing something in Hawaii to fill Hawaii up. And so we're sort of making progress, making this nationally. And now, in addition to be eligible for this sort of innovative program, we had to define innovation thrusts. And out of those innovation thrusts, 3 really turn PRP into NRP and sustain it into the future. And 2 more are totally new and different. And so the 2 more that are totally new and different is, we have in one of the sites in San Diego an innovative fabric that allows rack of hardware to be conceptualized as a single node connected via PCIe. So we basically can dynamically do what you would normally do by unracking a device and re-racking it into a different node. this can be done software controlled via something called a product by a vendor from called Giga.io. And so we use in order to compose NVIDIA GPUs with AMD CPUs and Xilinx FPGAs and NVMe in order to build unusual nodes that we can then see whether people can request unusually styled nodes that they can then experiment with, and maybe then buy nodes like this and add it somewhere in the country into NRP proper so that it is usable for the community. That's sort of the kind of idea that we're shooting for here. Secondly, we have the I2 thrust. We have innovative application libraries to expose FPGA hardware to science applications without having to be an FPGA programmer. One of them is machine learning inference. So there is a whole set of libraries that we will support in order to make machine learning inference available to people who can only program Python and not high-level HLS or something like that in Xilinx. Then the data infrastructure model for NRP supports everything that you've heard from Larry and Tom. In other words, it supports the concept of regional self-storage systems. A campus can join an individual storage host, just like a campus can join an individual GPU node into one of these storage pools. And then we are, in addition, deploying a replication system that's new to NRP. The notion is very simple. If you have regional storage and you're an end user, ideally you would like to say, here's my directory tree. There is the foo directory and the bar directory. The foo directory should be replicated between the southwest and the northeast, and the bar directory I only need in Chicago. And that's good enough, because I'm going to do all my work with collaborators in Chicago on their hardware, but the foo goes distributed across the nation. And that sort of thing should be user-controlled rather than system-controlled. And we will provide an interface like that. It's part of the development cycle of this project. Bottom line, NRP data infrastructure model combines the best of PRP and OSG and then throws something in that is totally innovative and new. And as a result of this, we're building out, in combination with other NSF programs, for example, the CC Star program just funded 9 different storage systems at campuses, in 9 different campuses. All of those will be integrated into this system if we get away, assuming the partners agree and want that. Now, science drivers, there's lots of AI in here, but also so much more. It includes NSF MREPs. It includes some big science, LIGO, IceCube, and DKIST. It includes campus-scale instrument facilities. We have a special focus here on integrating instruments because we believe that instruments are the data producers, and if you're forming a network data-heavy infrastructure, then you want to integrate the producer of the data into the infrastructure, and that's where the instruments come in. The instruments then, of course, come in with all kinds of interesting science and interesting anything from machine learning to or more conventional things. And then we have a bunch of different types of sciences. We literally asked, the choice of the science driver was to build a matrix. You have the innovation thrusts and you have the domains. And we try to build a matrix across these 2 dimensions is such that there's a fighting chance that you have sustainability via people sustaining each other because there's mutual sets of interests. A guy from CS with somebody from molecular dynamics have a common innovation interest, and therefore they form mutually supporting social networks and infrastructure. That's at least the idea, and we'll see how well that works. And that goes back to the matrix channel chats that you've heard from Larry and Tom about. That's sort of the concept. Now, I'm a physicist, I'm a data guy, I like numbers. So I like to set goals that are hard to achieve, but not completely crazy, but are quantifiably verifiable. And so what we set as goals is the NSF funds us to the tune of 280 plus 64 GPUs, whatever that number adds up to, 300 and some GPUs. By the end of deployment in end of 2022, I want to have 1,000 GPUs on the platform. So in other words, roughly 3 times as many as the NSF has supported with money. So in other words, 2/3 of the total number of GPUs come out of the community. That's what makes it a community infrastructure. The NSF funds about 5 petabytes of storage via NRP itself. There's another 5-ish, 10-ish or so via other projects that we either Tom Lair or I are PI of. And so let's call it 10, 15 petabytes that the NSF funds us for. I want to, by end of 2023, want to hit the 50 petabyte mark. And how do I do this? It's all community. So the community helps us build this. We build it with the community for the community. That's the idea. And we'll see how much growth we can actually make happen and what actually really happens. Then we want to introduce new capabilities in the NRP. There's machine learning at the 100 terabyte scale. Right now, we do basically machine learning at the single node level. Single nodes have a few terabyte max of NVMe, and that sort of sets the scale where we max out. This interesting new fabric that is in the San Diego site has 350 terabyte of NVMe. So we can actually start doing multiple 8 GPU DGXs from NVIDIA, hitting 300 terabyte of NVMe, and do interesting things with this, and hit 100 terabyte AI at that scale. And I'd like to see that happen, and we just haven't found the right combination of use cases and technology drivers. We want to expand with new types of nodes. We want to expand into wireless edge IoT. And we want to see new directions initiated by the community itself. You guys in the community should come to us and say, what you have here, I could actually use to do something completely different, X, Y, and Z, or I could bring to your infrastructure A, B, C, D, E, F, G, and therefore do something really novel and different. We want to be open for that kind of thing. And see you all at the 4th NRP workshop in San Diego on February 8th to 10th, where we will discuss this further. Thank you very much.
Gentlemen, if you have a minute, I've got certainly one question, maybe 2. All right. So I'll start with the premise is that if you want to take this wonderful technology, innovation, and community and have it live beyond the 10 years and all of our retirements and make it global, you have to transition some part of the core essence from relying solely on NSF funding to leveraging the NSF for building, scaling, growing. So has there been talk about establishing a membership or consortium model, thinking of Scenic itself, Los Netos, Globus, the Research SOC, Internet 2? Has that been part of the vision?
Wait. Of all the words that the agencies throw around, the word sustainability is the most abused. Let's start with that. Because you can't sustain anything without money. And so, first of all, I totally acknowledge the problem. Now, yes, we've actually had that discussion. In fact, my personal involvement with Internet 2 started by me going to Howard soon after he became a chief of Internet 2 and asking, is there stomach for doing things like this in the context of Internet 2 in such a consortium-style way? So it's clearly on the agenda. Is it the way to sustain beyond the 10 years? I think the only way that you can sustain anything like this is by being maximally opportunistic. You've got to try out as many different ways as you can think of, and then sort of bring melanges together and make salads and achieve a sustainability via this kind of salads. And part of the salad can be institutional support, can be federal support, NSF support, can be state funding, can be consortium model membership fees. And I would like to think that it ought to be industry funding to some degree. I think we should always have in mind how can we leverage collaborations with industry in such a way that industry pays the bill for part of what you're doing, because when everything is said and done, industry benefits from what you're doing, because we are the ones who produce the human capital that make profits soar. And that fact should lead to some amount of money falling back down in the waterfall back to academia in order to sustain things like this. So yes, we're thinking about it, but I think it's very complicated, and I am all for maximal opportunism when it comes to trying to sustain things like this.
Thank you, and I do agree that each of these things that I mentioned, they're all unique, and yeah, they all change through time, so thank you.
So this is going to get held together by software. None of us have the laptop we had 10 years ago. 10 years from now, none of this equipment, it's good for 5 years, right? So the nice part about what we've done is it allows machines to die and be replaced, and it's all the same software. And that's really what's going to hold it together for a very long time, I think.
I think one of the things you're going to see is we haven't really started a national effort in artificial intelligence and machine learning, and that is going to be current reports going into the OSTP, the federal government, is that the government will probably spend at least $1 billion in developing it. And I can remember when the first PC was delivered. And actually I got one and given to me by the IBM representative in Illinois in '83, because he had no idea what to do with it. And he thought maybe I could figure out something that he could help him sell a few more. So these things go through the same thing with the first smartphones and so forth. Now we're seeing development of IT and the edge devices and so on. But the thing that's going to require is the human trained workforce. And I think if a lot of other things are an example, California will be the leading state because of Scenics and now Golden State Middle Mile initiative to get this networked capability that is the underpinning of all machine learning and all of the California-wide multi-hazard warning systems that we're going to have. It's all going to run over the network. And because Scenic is the best regional optical network in any state, in fact, probably in the world, it means that more of our people will be able to participate in this. And that's why I think the real next 5 to 10 years is a vast expansion of the human participation. And I think it'll be national, it'll be international, but I believe you'll see California continue to be the leader in this, and that will end up because of Scenic and Golden State. Question?
The time, or we've got one more question?
Okay.
Okay, I'm trying to see if I can make mine really, really quick. So, from a network perspective, right, as we support the PRP or the future of the NRP, this is George from UCSC, by the way. As far as when PRP becomes NRP, and there's additional workloads probably expected on our systems, do we have anything predictive that might help us determine what sort of bandwidth utilization we might get over time?
Yeah, we have everything about the network use monitored, and so we actually work with a lot of the networking staff and the variety of the regional networks. We look forward to doing more of that. In fact, I just talked to the head of Scenic's engineering team, asked me if we could have a Zoom, Tom, and I said yes, of course, because they want to take this into account in their future planning and so forth. So we work very closely with the network engineers to try to be doing projections, and it's it's a lot like what happened with COVID, and no one expected to be the network traffic that was going to be needed for all the Zoom calls and everything else, but as it began to develop, the network was in fact flexible enough to handle that.
Thank you very much. Could you please consider expanding that to the UCs and other members of the cluster as well for the call? Thank you.
All right.
I'm not Jeff Weekly, and this isn't the first question, but my question is this. Two questions, really. One is, what is the minimum sort of requirement to plug into this, community?
Mm-hmm.
And secondly, can people or organizations outside of the U.S. connect?
I'll take the first one. It's containerization. So if it's anything like when my kids were in high school, Java had just come out as a programming language. And my son Joseph and his classmates in Illinois learned it on the street. And then they started making all kinds of applications in Java. They didn't learn it in school. And so I think containerization and the use of Jupyter notebooks and so forth is the new Java. It's the stuff kids are learning on the street. And they just, because it allows them to be creative. It allows them to share their creations across with other people. So that's the fundamental thing. This is all based on containerized software applications that then the open source Kubernetes that all of the world's clouds run on orchestrates. And so you've got to know that. And it turns out that a lot of current full professors don't have a clue. But fortunately, they have students. And that's what we're finding, is that you get the professor who has, or whoever has the idea, but the younger people, this is just their blood. That's just what they live in. So that's where, that's the entry fee. And then Tom, you can talk about the global.
Sure. So, for the global people, what we've expecting them to do, and they're doing, is create research platforms in their countries, just like they have research networks in their countries. And to the extent that we can share things that work, the databases, interconnect the Ceph pools, and so on, that's all fine. I'm a little sensitive to the fact the National Science Foundation is interested in funding collaborations, but doesn't want to fund the whole planet to do computing. And so but that's been working very well with Korea, Australia, Singapore, the Dutch, the people who, if you go back into the days of networking, are the ones who first put the networks in, and they're the ones that are pushing on this very strongly now.
Yeah, and the NSF has a long history of supporting international research and education networks. The half of it that comes from our country to the other country, and then the other country puts in their money. And it's all built on those R&E networks. And like I say, next month there's the third of the Global Research Platform meetings, and people from all over the world come to those.
Let me add one more vector to this that drives international expansion, so to speak, and that is large international science collaborations. So we have, by virtue of LIGO, LIGO really was the driver, or the gravitational wave observatory community was the driver of the caching infrastructure that I mentioned being global, because there is a real scientific necessity to combine the data of all these different gravitational wave observatories, of which there is now 2 in the US, 1 in Europe, one has just been commissioned in Japan, and one is planned for India. And so all of these observatories want to share their data. All of these communities want to and analyze their data simultaneously together, because it gives you pointing accuracy in the sky to where the wave came from. And so as a result, they want caching infrastructure, data infrastructure that is global. And so we right now, as of today already have inside the Nautilus cluster caches in Europe, Australia, Korea, and I'm probably missing some continent.
Netherlands.
There's Netherlands in Europe. It's
Europe.
Netherlands, Italy, Czechoslovakia, UK, and I'm probably missing some. Basically, the caching infrastructure and the need to have a content delivery network that spans the globe is driving globalization of Nautilus. The compute lags behind because people are much more reticent sharing compute across national boundaries, because within a federal budget or within a national budget, compute is paid for. And there's less of an incentive of sharing. Am I making any sense? And so there is only these large experiments are capable to say, I want to take in-kind contribution from Czechoslovakia to my experiment, therefore I need a cache, and then the CPUs that we have will be made available to that experiment. Voila, we're a game, and we can play. And it's those kinds of things that provide an additional globalization vector that we actually see and exploit.
And there's just one more thing that I would like to add that's along that line, and that is when including people directly into Nautilus is too hard, then we federate, right? And if they're using the same software approach, they're using Kubernetes, they're using Jupyter Notebooks, and they adopt a similar hardware profile, then it's very easy to collaborate, even though we might not be sharing resources.
Okay. All right. Thank you very much.
So let us thank our speakers on our panel.